Hey guys, if you are familiar with the Internet of Things, you know that there is an overwhelming number of IoT connectivity options. Each IoT application has its own unique requirements, so the IoT connectivity option that's amazing for one application may be awful for another one. Your application may require thousands of remote sensors, so the battery life is one of the critical considerations. Your application may need to send lots of data, like audio video data, so high bandwidth is one of the essential factors. Or your application may involve life or death decisions, so the time is the primary consideration. So you will agree that it's a crucial thing to choose the best IoT connectivity option for your specific needs. The three basic parameters, power consumption, range, and data rate, are interrelated. You can only pick two of them in your favor. I know it's an inconvenient truth, but it's reality. We have short range technologies like Bluetooth and Wi Fi offering very low power consumption and high data rates. Yeah, very good. But the Internet of Things needs wide area connectivity like networks across cities, not just across your office. Bluetooth and Wi Fi might well become the dominant IoT connectivity tech for the home and office, where the connectivity above a few meters is unnecessary. For longer range applications, you have to look elsewhere. How about GSM, GPRS, 3G, LTE, 5G? Yeah, these technologies operate over several kilometers. They also offer high data rate, so voice and video streamings are possible. Brilliant, only if you need voice and video streaming. Hint, you almost certainly don't. GPRS modems cost around $10, 3G modems cost $25, and LTE modems are up around $50. So what if an application requires long range and low power consumption? So we come to the third option, which is low power wide area network, LPWAN technology. In this video, we'll provide the comprehensive overview to a class of IoT connectivity known as LPWAN. So the first question, what is LPWAN? Is it a standard? The first thing to understand is that LPWAN is not a standard. It's a broad term consisting of various implementations and protocols that share common characteristics as the name suggests, low power and wide area. Low power means it operates on small inexpensive batteries for years, and wide area means it has an operating range that is typically more than 2 km in urban settings. But, as there is always a but, a physical limitation to achieve low power and wide range is small data size. Most LPWAN technologies can only send less than 1000 bytes of data per day, or less than 5 kbits per second. Now you'll ask me, but bro, we have fully developed and working stacks of protocols such as BLE, Bluetooth, Wi-Fi, Zigbee for IoT. We have a freaking 4G for long range connectivity up and running. Why on the earth do we need LPWAN for IoT now? Well, we do. That's because Bluetooth and to some extent wireless LAN and Zigbee can't throw out the data that can be heard at kilometers away. And cellular networks are expensive and consume a lot of power. And we rarely need the kind of speed they have to offer. So effective bandwidth utilization is an issue for IoT applications using cellular connectivity. And that is why LPWAN is perfectly suited for applications that want to send tiny amount of data over a very long range and depend on battery for power. Now you may take a look at more use cases for LPWAN.
Now let's go back in time to understand how LPWAN was born. As can be seen in the timeline in front of you, a span of interest dates back to 1990s and it unfolds till date. We will take a look at each section of this timeline one by one. In the late 1980s and early 1990s, there were similar topologies and network architectures. However, they were not named LPWANs. Looking back, they are the predecessors to this movement. Now let's take a look at what happened in 1990 till 2000. The example analogous to today's LPWAN was developed by Alarm Device Manufacturing Company. It is also known as Ademco. It was called AlarmNet and it monitored alarm panels. It transmitted very small amount of data over 900 MHz network built by Ademco. AlarmNet networks operate in 18 major areas around the US and cover about 65% of the urban population. Honeywell owns the company now. Another example is of RDIS. It was built specifically for data-only applications. It was a wireless wide area network owned by Motorola in the 1980s. It was relatively low-speed network used primarily for sales automation, fleet tracking, email, and other applications. It was absorbed by American Mobile, who picked up the RDIS customer base and migrated them to later technology. Wanna know what happened in 2000? As the calendars moved to the turn of the millennium, cellular networks identified that voice can also be moved with data. In that way, 2G was born. Many alarm panels and similar systems migrated to cellular network. Later, 3G allowed high-speed data transfer over long distance. All was well, but power consumption was still an issue. Power consumption was still not as low as we would have liked it to be for an IoT application. And around 2000, folks got aware of the necessity of low-speed, long-range connectivity scheme that wasn't power greedy. We can call it re-emergence of LPWAN. More and more things were getting connected and not all of them needed to send truckloads of data. Most of them, especially those deployed somewhere wirelessly, had to see their lives ticked away to limited battery they had. A French startup named Sigfox, founded in 2009, cashed in on this and developed the connectivity scheme which we can call modern LPWAN. Since then, we are having increasing involvement in low power wide area connectivity landscape. Currently, we have multiple groups such as Sigfox, Ingenu, members of LoRa Alliance and others, all creating LPWAN technologies. These groups are building relationships with solution providers and working on the use cases such as asset tracking, building management, smart cities, and smart agriculture. Okay, enough of history now. Now we are gonna go full technical from here. So, fundamental LPWAN concepts. I tell you, this part is gonna be a bit boring. Okay, first of all those boring concepts is processing gain. It is ratio of radio frequency bandwidth to the unspread bandwidth. It can also be defined as signal to noise ratio of processed signal to that of unprocessed signal. To be more clear on this, please check the example given in slide. It says if 1 kHz signal is spread to 100 kHz, the processing gain would come out to be 100, or in decibels, which is how it is usually expressed, it will come out to be 20 decibel. Bandwidth versus range. Here we have a little graph to see where LPWAN stands in comparison with other technologies. On y-axis you have bandwidth required and on x-axis you have range capability. As you can see, LPWAN sits far right on range capability and it sits very low on bandwidth required. So what it means? It means that LPWAN is capable of achieving high range and at the same time it requires low bandwidth, which means we can use it for the applications which need to send tiny amount of data over long range. Observe where other technologies lie in the same graph. As you can see, none of them are able to offer the range capabilities of LPWAN. Range versus data. LPWAN has been envisaged with long transmission range in mind, but longer the road, more obstacles in the way, no? So how do we make our signal live through all those obstacles? The answer is high transmission power. Makes sense, right? For a high power signal, it won't be that easy for obstacles to fade it away. In an obstacle-free medium, you still need the signal with high transmission power to not die out in the middle. So, even though we use signal with high transmission power, the signal might just go weak when it arrives at the receiver. And we want our receivers to be able to detect these weaker signals too. So, LPWAN uses this high sensitivity receivers which typically have sensitivity higher than minus 130 dBm. Technologies with minus 130 dBm can detect signals 1000 times weaker than technologies with minus 90 dBm. So you can see how important this is for LPWAN. Noise versus bandwidth. Let me first introduce you to the concept of noise floor. Noise floor is the measure of the signal created from sum of all the noise sources and unwanted signals within the measurement system. Well, noise is any signal which is not the signal which is being monitored. So, how it affects our channel? Well, the bandwidth and noise influence the noise floor, which in turn influences the SNR, which is signal to noise ratio. And it has been established that narrower the channel, we get lower noise floor. So it is easier to detect the signal. And in LPWAN, we usually have narrower channels or coded channels. So it is easier for the receivers to detect the signal even though they are at distance. Interference. Just now I mentioned that in LPWAN we use either coded channels or narrower channels. So how does that matter here? Well, theoretically, coded channels and narrowband channels offer same performance in presence of interference. Well, it is a long-standing argument in this field whether to use coded channels or narrowband channels or something else. So even experts can't agree upon one single solution. So yeah, I'll just leave it there, like the experts. Licensed versus unlicensed. Most technologies in LPWAN space use unlicensed band, and they work fine in licensed band too, but cost has to be paid in terms of reconfiguration of medium access control schemes. However, there is a problem of spectrum availability for LPWAN technologies using 800 and 900 MHz spectrums. Also, there is no specially allocated band for LPWANs anywhere globally. There is more localization capabilities. This thing doesn't end. So, localization capabilities is about locating where the RF signal came from. So, it is just converting the time of arrival into direct path length. For that, you need two things: enough power on received signal and enough bandwidth. But as most LPWAN technologies are not received on direct path, they come bouncing off one and the obstacle to the receiver. We don't have enough power on the received signal. So this is a limitation, and you may go to the other technologies for better localization capabilities. I hope that was it. Orthogonality. Hey man, I'm done. You said it won't take this long.
No, you have to do it. This is the last one for you.
Okay guys, this is the last one that I'm gonna explain. So, orthogonality. You've heard this term from linear algebra or geometry. When two lines are orthogonal, they are at right angles to each other. So RF world just borrowed this term from mathematics, and in RF world, orthogonality is when you have two detections of two different signals at the same time. So orthogonality is detecting multiple data streams in the same channel at the same time. So these are the fundamental concepts of LPWAN, and from here my friend will take on. Now the time has come to discuss top LPWAN technologies and platforms. Here we have Link Labs, Enwave, Ingenu, Sigfox, Weightless and LoRa Alliance. However, we are going to focus on Link Labs, Sigfox and LoRa Alliance. Link Labs. Link Labs build hardware that supports the LoRa Alliance standard but also developed a proprietary system to provide more advanced functionality. It is called Symphony Link. It uses LoRa physical layer but does not use standard LoRaWAN MAC architecture. It has range that is 100 times that of Wi-Fi, and it is cheap in comparison with cellular networks. The Symphony Link gateway has 8 channels and it operates in sub-GHz domain, and it is ideal for industrial and municipal monitoring applications. The link transceiver modules usually operate in 915 MHz ISM band. The positives are many miles of range and flexible technology. The long range has been supported due to the high sensitivity receivers. Sigfox. Sigfox sets up antennas on towers and receives data transmissions from devices like parking sensors and water meters. These transmissions occur in 868 or 915 MHz bands. Sigfox's wireless systems send very small amounts of data very slowly. So, they offer them long-range capabilities by virtue of Shannon-Hartley theorem. So, this technology is good fit for any application that needs to send small data and at very slow speed. Things like basic alarm system, location monitoring, and sample metering are the examples. But there is one drawback, which is they are not battery friendly. That is, for battery powered devices, we won't be suitably able to use this technology or platform. LoRa Alliance. LoRa Alliance promotes an open standard for LoRa-based networks called LoRaWAN. This standard was developed by Semtech, the owner of the underlying chip technology, IBM Research and Actility. LoRaWAN offers functionality that is very similar to Sigfox. However, LoRaWAN standard lacks features that are important for some customers. They include roaming, packetization and retry, disconnected operations, quality of services, firmware upgrades over the air, and repeaters.